Hello everyone, this is Sunbeam. Right now I'm not using the standard method of recording audio, so I'm using a desk microphone that doesn't sound as good as the headset microphone, and you may hear some tapping sounds or stuff like that when I'm going to use the keyboard. But anyway, this short video hopefully is related to one curiosity that I had across time. It's related to Assassin's Creed Unity and Assassin's Creed Syndicate. Both of these games had an interesting feature to them in the sense that Ubisoft decided to implement integrity checks in such a way that whenever you were modifying any executable memory, you would not be able to run the game. Basically, the game crashed if you attempted to modify that executable memory, and that was because, well, they were scanning memory. And at the time, like 4 or 5 years ago, or maybe more than that, there weren't any proper methods, so to speak, that basically bypassed these checks. And starting with the Mortal Kombat 11 attempt to bypass the various integrity checks that those folks implemented, and well, starting on this path, on this little crusade, kind of got me interested in what I can do if I went back in time and took a look at Assassin's Creed Unity. So I basically got the game, installed it. It was free at some point ever since that Notre Dame tragedy that happened, and tried to look a bit at it. What do we know about it? If we take a look at with the CFF Explorer at the executable, we can easily spot the fact that these guys may use either, well, not either, just VM Protect. And the way to spot this is that there are two sections very close to the last section in the executable that are named identical, but difference is the 0 and the 1. If you attempt to modify anything in this file and you try to run it, you'll see that you'll receive some errors regarding file integrity checks. So they have those in place as well. But let's see what happens when we run the game. And then with Cheat Engine, with Cheat Engine we modify 1 byte in the game's memory, whichever byte that is. So ACU, we go here, whatever, and ACU.exe, and let's say we make this execute read write. As you can see, changing the page protection doesn't do anything. But if we change this byte from 44 to something else, like 01, there we go. The game basically died. And that is because the integrity checks kicked in, the active integrity checks kicked in. And as you can see, they do not verify only the executable code, but the entire memory space that this game's executable occupies. Let's try to run it again and see what happens there. Who exactly, or what piece of code is actually accessing that byte that I just modified? That's the logical way to go at it. Keep in mind that I'm using Cheat Engine's vectored exception handler debugger, so the vec debugger, and I'm going to do the same thing, go here, whatever, and then I'm going to find out what accesses this address. And as you can see, something is constantly reading this 7, 8, blah blah blah. Now, normally what people try to do at the time was to modify this particular instruction in such a way, or I don't know, just tap into this jump here or the jump above, or no, not the jump above, the jump that leads to this instruction, in such a way that rerouting this jump to your function would basically restore the cyclic redundancy check, the CRC check, the CRC value for that particular memory location that you modified. So what this function that's constantly reading the byte does is to basically sum up the bytes, or apply a formula that contains operations with each byte. So with this one, this one, this one, and so on and so forth, up to a certain point, and expects, as a result, a certain value that comes out of the calculus. That value is then checked at the end of the check, and if the value is different, well, the game crashes. It's very simple in theory, but in practice, that value is shielded into vmprotect mutated or virtualized code. So it won't be as simple as looking for a compare somewhere in the code like CMP register value. You will not find it that easy, or if it is, it's put in a different form, but you'll have to figure out to interpret where that particular check is. As you can see, the counter is incrementing, so if I'm changing this byte, as you've seen earlier, the game will crash. But what I thought was, why not, instead of and I'll get back to that. So the method people tried was to modify this jump to go to a certain section where they can manipulate the data in such a way that this byte, if I change it to 0, 1, it will still be 4D. Now you see it better. So I changed this to 0, 1, and I want the game to think that even though I put this 0, 1 here, well, it will still read 4D. So that's what pretty much people were doing in their actual function, their actual cave. They were making the game think that the byte that the protection reads is the original one, not the modified one. The problem was, even this code here, even this location, this address, Control G, and if we copy this and we go here and then we try to see what accesses this, you'll see that this one is also accessed by a certain other location and by a certain other location, and so on and so forth. Now if I take this one again, then it will be accessed by another location, and so on and so forth. So it's basically a tree of functions that are checking one another. So in order for you to defeat this check, you would have to hook each and every function that you find in here, and this is a tedious task, because sometimes the developers might be sneaky in the sense that they would create timed checks like these. Like for example, these checks would come out like 5 minutes into your gameplay, and then you'll wonder why the game crashes. But considering the code that is accessing the, let me also show you what's going on here. It's pretty much similar code. As you can see, the assembly is very spaghetti-like, which means this is most likely vmprotect code. So this code that we're looking at, this assembly that we're looking at, is part of the vmprotect's integrity check routines. But who says we need to actually deal with vmprotect? We only need to deal with something that will not check this area, not this area, this area, where we have our code. For example, if I look at this document here, I see that I'm scanning for an array of bytes, and I have one result. I'll go there, and this is where I basically want to place a hook. And what I did was to use a harder breakpoint that Cheat Engine would place atop this prologue here, in such a way that I can read the RCX register. But if I take this piece of code, this location, right, and I go here and I try to see who accesses it, I see that the only thing accessing it is this particular piece of code here. And now, if you remember the Mortal Kombat 11 talk that I had in the beginning of this video, well, if you stop this, you go to this particular location and then you press F5 so the debugger breaks here, you'll see that it did break. If you press F9, you'll see it still breaks. But if you look up top here in the bar, you see currently debugging thread 266C. You don't see any other value. So the next step for me would be to go to x64dbg, in which I have a plugin that deals with attaching and VM protect checkups and shit like that. And we're in, I think. Well, we're in the game. The game might pause at some point. Or not, depending on how the graphics libraries update. Okay, go here. Take a look at the breakpoints. No breakpoints. Well, we're attached to the game. So, if you remember when I set the breakpoint here, cheat engine would break and the thread was 266C. So let's take a look at the threads. That's why I made this video. 266C. You can see that this has a thread entry. And if you look at the code, it's pretty much spaghetti. So, what happens if I go to threads, take this thread, and I just do kill thread? Thread is gone, right? Let's now take a look at who's accessing my code from earlier. And, well, as you can see, nothing is accessing it anymore because, well, I killed the, let's say, anti-tamper thread. So right now here I can do whatever with this particular location because the game will not crash anymore. I can also do what I did earlier. So let's stop this, go to acu.exe. You can change this byte. That will not affect game flow or process running. Let me just change the protection first. Read, write, execute. Now I can change this to 01. And as you can see, the game is still running. So my question now is, why hasn't anybody fucking thought of killing that check thread 4 or 5 years ago? And everyone has created trainers that are dealing with harder breakpoints and shit like that, and convoluted methods that I explained earlier, trying to patch one check, then patch the other, then patch all of the checks in such a way that they don't check one another, when all of this could have been resolved by killing just the thread that basically checks our executable code, the part of the game executable that we want to modify. So there you go. Now you know how to bypass the famous Ubisoft anti-tampering checks in 2 of their titles, Assassin's Creed Unity and Assassin's Creed Syndicate. For some of you, these games may be obsolete and, well, who plays them anyway, right? But it's the protection that mattered, and this is something that that has been puzzling me. And, well, thanks to the Mortal Kombat 11 bypassing stuff checks, threads, discussions, and so on and so forth, well, thanks to the Nouveau and the methods that we use there, I thought of, well, deviating a bit from the standard process and get back to these 2 titles in such a way that I figure out how exactly the protection actually work here. That's, well, de Nouveau, it's mostly based on VM Protect, just in case you didn't know. So, having said that, thanks for watching, and, well, this is the way you bypass the protection, the famous protection in Assassin's Creed Unity and Assassin's Creed Syndicate games from Ubisoft. Talk to you later, bye!